you taking organic chemistry this summer? You are, don't go anywhere. We're doing some predict the product practice problems. So this is one I posted as slides 2 days ago. I've been kind of sick on and off, so I haven't been able to post as much the last like week or so. Sorry about that, guys. But I'm back. I'm feeling better. Let's get through this. So this is one that I posted the other day. Like I said, we have this benzene with methoxy on it. And we're going to do a Friedel-Crafts acylation. I'm sorry, alkylation, not an acylation. Where we have this chloropropane and we have trichloroiron. And of these three right here, which one are we going to get? If you want, stop, pause the video right now, work through it on your own, come back. If not, let's work through it together. Okay, so we have our starting materials here. I'll zoom in on this a little bit. First thing that happens is with our chloropropane and our iron trichloride is that forms a bond there. And what that does is this gives this a negative charge and this gives this a positive charge. It coordinates. And this chlorine does not like having a positive charge. It's pretty electronegative. It does not like that. So what it does is it kicks off electrons from that bond there. And we are left with a carbocation on this primary position here. Now, if you've been following along with any of the videos, or if this is not your first time on organic chemistry, you know that that carbocation is not very happy right here at this position because a carbocation is more stable in a more substituted position. So what isn't going to happen is it's not going to grab it here and form that product. What's going to happen is that carbocation is going to move in a hydride shift, and it's going to shift to that secondary position, giving us, that's terrible, carbocation, giving us a secondary, better, carbocation. And so this is then what our EAS is performed on, is Friedel-Crafts acylation, which is a type of electrophilic aromatic substitution. It's going to come in there and grab that there. So it's going to come grab that. The only thing we have left to figure out is where is this going to end up on this ring? So we have a methoxy group here. A methoxy group is what's known as a donating group. It activates the ring because it has electron density because it's oxygen that it can donate into the ring. And because of that, it's what's known as an ortho para director, with these being the ortho positions and this being the para. So it directs the group coming into these positions. Well, which one is it? In reality, you're going to get a mix of both. But for the sake of this, and for most exams, it's usually what is the major product. So we're going to go with the major product. So even though there are two ortho positions, because this methoxy group, remember, it's going to have hydrogens on it as well, like this. And this can move. This is actually sterically bulky. So this position right here is blocked a little bit. So the easiest way for it to come in and grab this is from the para position right here. So the major product that we're going to end up with is we're going to end up with this right here. That's a terrible benzene ring. I'm sorry. Where we would have, I'd say this is 1, 2, 3. Say this 4 isopropyl, 1 methoxy benzene, or I guess you don't count the iso in the naming, so it would be 1 methoxy 4 isopropyl benzene, or what you can call it is para isopropyl. Sometimes you use the para. Actually, let's not do that right now. It's just confusing. But that's how we get that there. I'm not going to do it right now because it's a little more in depth, but I have made a video on ortho para directors and why they do what they do. Okay, so like we said, because there is that carbocation shift, And then this methoxy is a ortho-para directa with the ortho positions being slightly blocked. That it's going to add para, and we're going to end up with this 1-methoxy 4-isopropyl benzene. So A is the correct answer.